צהריים טובים לכולם, ברוכים הבאים. אנחנו עוד רגע נתחיל. צהריים טובים לכולם, ברוכים הבאים. אנחנו תכף נתחיל את הוובינר בעוד רגע. צהריים טובים לכולם, אנחנו נתחיל ממש עוד דקה. מוזמנים לפתוח מצלמות מי שרוצה, אני אשמח לראות אתכם. האחרונים ממש שמצטרפים אלינו ואנחנו נתחיל את הוובינר. טוב, אז אנחנו נתחיל את הוובינר שלנו. אני אגיד בתחילת דבריי שאנחנו נקליט את הוובינר, כדי שכל מי שלא פה יוכל לקבל את זה, וגם אתם תוכלו אחרי זה לצפות בו שוב. אז ברוכים הבאים לוובינר שלנו על פאנל מתודס, על תוכנה שנקראת FlightStream. מי שלא מכיר אותי, אני שמוליק, אני מוביל תחום האירוספייס ודיפנס פה בישראל ובדרום אפריקה. נמצאים איתי פה בוובינר גם שני קולגות שלי, דוקטור ויבק האוג'ה, who is the director of the FlightStream globally broadly, and תומר אדר, שהוא application engineer שלנו פה בישראל בדרום אפריקה, מטפל פה בלקוחות, חלקכם גם מכירים אותו. אנחנו נדבר על הטכנולוגיה ועל הערך שיכולה לתת, אבל כמו שגם אמרתי קודם, אנחנו נקליט את הוובינר. חשוב לנו שתעלו שאלות, הרבה פנו אלינו מראש, אמרו מה זה אומר ואיך זה אומר, חשוב לנו לוודא שאנחנו ניתן לכם מענה להכל. אבל תרגישו בנוח לאורך כל הוובינר, לרשום שאלות פה בצ'אט, וככה תומר וגם דוקטור ויבק יוכלו לענות על השאלות שלנו פה. אז מה הולך להיות לנו פה היום? מבחינת אג'נדה ומה שהולך להיות, אנחנו קצת נעשה איזושהי סקירה רחבה יותר על מה שקוראים בעולם הזה, משם נצלול לפלייטסטרים, נעשה איזשהו overview רחב, ומשם גם ויבק יציג לנו דמו על התוכנה עצמה ואיך שהיא בעצם פועלת. כן, אני מבקש שתשימי על מיוט כדי שלא נפריע לשיחה. טוב. אז בשתי מילים על אלתר, מי שלא מכיר את אלתר, אלתר היא חברת תוכנה אמריקאית שנמצאת בשוק כבר כמעט 40 שנה ומחזיקה תוכנות וסימולציות בעולמות של אנליזה, עולם המכני, האלקטרומגנטי, זרימה, כלים בעולמות הדאטה והאנליטיקה וגם ה-HPC. היא נמצאת בעולם של המחשוב מתוך הבנה שחברות צריכות כלים יותר ויותר מתקדמים שידעו לתת להם ערך. הרעיון העסקי שמוביל את אלתר זה שחברות הנדסה יש להם מספר אתגרים שמתחברים ביניהם, גם הנושא של הסימולציות, גם ההבנה שצריך להביא תובנות ולכן צריכים כלים בעולמות הדאטה והאנליטיקה, וגם יכולת לעשות upgrade לכוח המחשוב שלנו ולהביא שהוא תהליך שהוא משותף. ובשביל זה מחזיקים מעל 150 כלים שנגישים היום ואפשר לעבוד איתם ונותנים ערך משמעותי ללקוחות שלנו. לאורך הדרך מתוך ההבנה הזאת, אלתר עכשיו והטמיע עוד ועוד כלים ועוד טכנולוגיות בעצם שמביאות ערך משמעותי ללקוחות שלנו. כלים בעולמות האלקטרוניקה, האלקטרומגנטיקה, כלים בעולמות הדאטה והאנליטיקה, כלים בעולמות של Additive Manufacturing, והרכישה האחרונה והאקוויזישן האחרון זה FlightStream, כטכנולוגיה שיודעת מענה מאוד מאוד משמעותי לעולם ה-CFD בכל מה שקשור לפאנל מתודס. אנחנו היום בסשן שלנו פה נדבר בעיקר על זה, ואני אתן עכשיו לתומר את הבמה כדי לבוא קצת לספר לכם על הטכנולוגיה. תרגישו בנוח, כמו שאמרתי מקודם, לרשום שאלות בצ'אט, אנחנו נשמח לתת לכם מענה בסוף הסשן. בבקשה, תומר.
תודה רבה שמוליק, שלום לכולם, תומר אדר, חלקכם מכירים אותי, תפקידי פה בכוח, באמת Application Engineer, כלומר כל השיח הטכני, איך התוכנות עובדות, למה הן טובות ומה הן עושות. אני אדבר קצת בקצרה על אלתר הגדולה, לפני שאנחנו מצטמצמים פה לפוקוס של היום, תכירו את עולם ההייפרוורק של אלתר, זה בעצם השם הכולל לכל תוכנות הסימולציה ודיזיין שלנו, שבעתיד הקרוב אנחנו מקווים שלכולן יהיה גוי יחיד, כלומר למדת התוכנה, למדת את כל השאר. מעבר לכך אני יכול לציין פה בקצרה שיש לנו יכולות סימולציה לכמעט כל פיזיקה שניתן לחשוב עליה. בחלק התחתון בצד שמאל אתם יכולים לראות את עולם ה-CFD שבו אנחנו נתמקד היום, ליתר דיוק בפאנל מתוד. בעולם ה-CFD באופן כללי ובאלתר בפרט יש כמה אפליקציות שונות. הראשונה שאנחנו נציין זרימה פנימית, שזה אנחנו מכירים מעולמות של טרמיקה ושאיבות ודברים מהסוג הזה, סלושינג ואוילינג, העולמות של SPH, כלומר spherical particles, טרמיקה וחום למול מכשירים חשמליים, ועולם המרכזי של FlightStream, אווירודינמיקה חיצונית. אז מה זה בעצם FlightStream? FlightStream זה השם של התוכנה החדשה לפאנל מתודס. מי שמכיר, מי שלא מכיר, פאנל מתוד טכנולוגיה חדשנית בעולם ה-CFD, FlightStream לוקחת את הטכנולוגיה הזאת ובונה על גביה עוד כל מיני פתרונים דיוקיים כאלה ואחרים, כדי להגיע לרמת דיוק מאוד מאוד גבוהה. אז פאנל מתוד, למי שמכיר או שלא מכיר, זו שיטה שבה אנחנו לא מתייחסים לנפח הזרימה כנפח בקרה, אלא אנחנו מתייחסים לגוף העובר בנפח כפאנלים. אפשר כמובן לפרט על זה הרבה יותר במתמטיקה, אנחנו לא נעמיק בזה יותר מדי. הכוונה היא שההתעסקות העיקרית היא למול הגוף ולא למול נפח הזרימה. מעבר לכך, בפלייטסטרים עצמה הכנסנו את האפקט הוויסקוזי, כדי לחשב את שכבת הגבול ולהגיע לדיוקים באקסטרפולציה לשארית הנפח, מבלי לוותר על המהירות של פאנל מתוד. אז כמו שאמרתי מקודם, אנחנו לא מתעסקים בנפחים, אנחנו מתעסקים במשטחים החיצוניים של הפלטפורמה שלנו, פלטפורמה מלאה לאווירודינמיקה חיצונית, ככה שאנחנו מרשתים את הפלטפורמה עצמה, ופלייטסטרים כבר מנפח את המידע לתלת מימד. כמובן שהאפליקציות מאוד מאוד נפוצות, בארץ אנחנו בעיקר מדברים על Aerospace ודיפנס, זה רלוונטי גם לעבודת מרים, עבודת אוטומוטיב, טורבו משירנרי, הכוונה למנועי טורבו, וכמובן טורבינות ענק. בוובינר היום אנחנו נתמקד באפליקציה הראשונה, Aerospace ודיפנס, תכירו שקיים בעוד מקומות. אני רוצה לדבר ממש בקצרה על נושא הדיוק של CFD ושל פאנל מתודס בפרט. כמו שאתם רואים פה בטבלה, אנחנו יכולים להסתכל ולראות את העולם של ה-Low Fidelity, בין אם זה אנליטיקה או משוואות אוילר, ויש את ה-High Fidelity, שזה ה-RANS ו-LES ו-DNS שאנחנו מכירים מתוכנות עבר ומהלימודים, ולאחרונה התפתחה שיטה החדשה המתקדמת הזו שנקראת פאנל מתוד, שהיא נחשבת Mid Fidelity, כלומר מאוד מהיר ומדויק עד כדי. בעצם כש-Research in Flight פיתחו את הפאנל מתוד שלהם לפלייטסטרים, והלבישו על גבי הפאנל מתוד את כל עולם הוויסקוזיות ועוד כל מיני דיוקים כאלה ואחרים, הרמנו את רמת הדיוק לעד כדי 1-2% מ-RANS, מפוטרני RANS. כלומר, עם הזריזות של פאנל מתוד, יחד עם הדיוק שמאוד מאוד מאוד קרוב ל-RANS. וכמובן, בעזרת GPUs אפשר להעצים את המהירות. בנוגע לשיטת הפעולה, או סליחה, אזור הפעולה שפלייטסטרים נמצא בו, אז אנחנו נמצאים בכל ה-flow regimes, כרגע החלק המתקדם ביותר עדיין בשלבים ראשוניים, אבל אתם יכולים לראות פה שמבלתי דחיסה ועד היפרסונית, זה העולם של פלייטסטרים, כרגע טרנסוניק וסאבסוניק בשימוש נרחב, סופרסוניק כרגע בשימוש התחלתי, וההיפרסוניק בשלבים אחרונים של פיתוח. בנוגע לאפליקציות הרלוונטיות, אתם יכולים לראות פה מהתמונות דברים שכבר יכולים לגרות לכם את המחשבה למול מה שאתם עושים בבית, אבל אני גם אתן את הדוגמאות עצמן. אז לדוגמה, שכבות גבול, חישוב שכבות גבול, בעיקר בהקשר של טורבינת אינטייק, כן? אנחנו רוצים לוודא שהטורבינה מקבלת מספיק אוויר כדי להפעיל לנו לחץ, בפאנל מתוד סטנדרטי אנחנו לא יכולים לראות את הוויסקוזיות, בפלייטסטרים ניתן לראות את שכבת הגבול ולדעת כמה היא פוגעת לנו באינטייק. כמו כן, ניתוקי זרימה בזוויות גבוהות, לראות באיזה זווית ובאיזה מנח הכנף שלי מתנתקת, כנ"ל לחלקים נעים, כלומר אני יכול לקבל חישובי זרימה על גבי חלקים נעים, בזמן הזרימה, תנועה בזמן זרימה של המדף, או של הסרבו, או של האיירלוין, לאורך הזרימה. כל זה כולל חישובי hinge supports, חישובי עומסים על גבי הצירים, על הסרבואים עצמם, וכמובן על המבנה. מעבר לכך, אנחנו יודעים לחשב high lift devices, זה די פשוטו כמשמעו, כל מה שקשור בהנעת סילון, הפענוח של הנעת סילון בשטח חתך ובנפח חתך, וגם פרופלרס במובן של מפל לחץ בשטח דיסק מסוים, ובמובן של כנפיים שנראה עוד מעט. אז כמו שאמרתי, יש את עולם הפרופלרים או ה-time domain, במילה היותר כללית, כל מה שקשור בתנועה לאורך זמן ולא רק מצב מתמיד. אז אנחנו יכולים לראות פה ריחוף של מסוק, אנחנו יכולים לראות כנף נוסעת, וכמובן Downstream effects בחלק התחתון. על כל זה ויבק ידבר בהמשך בתוך התוכנה ויציג איך זה נראה. לאפליקציות הדיפנסיביות או אפליקציות נתיקים למיניהם, יש את עולם ה-6-דוף, עולם 6 דרגות חופש, גם את זה אנחנו נראה בתוך התוכנה בהדגמה מדויקת. כל מה שקשור בהפרדת נתיקים מתוך פלטפורמה, או בשינוי הפלטפורמה לאורך הזרימה, כמו שאתם יכולים לראות פה את הדאבל קופטר שמחליף את כיוון הטיסה שלו מהנעה קדמית להנעה ריחופית. להרבה מכם שיצרתי איתם קשר מראש ובלי קשר שיצרו איתי לפני, דיברנו על FSI וכל העולם של עומסים ופרפור. FlightStream יודע להתממשק למול כל פוטן חוזק חיצוני, כמובן גם עם אופטיסטרקט של אלטר, ובהמשך יהיה גם חיבור ייעודי בין הדברים. אנחנו נראה הדגמה של איך מייצרים את ה-workflow הזה של ה-FSI, ואתם יכולים לראות פה שנעשו מחקרים רבים בנושא הפרפור וגם ברמת הכנף מלאה עם 10 פרופלרים. דבר נוסף שפלייטסטרים יודעת לעשות זה לחשב את האקוסטיקה ואת האווירואקוסטיקה שמייצרים ההנאות שלנו, מייצרות הפלטפורמות שלנו, לכל מצב שלא נצטרך, כולל גרפי DB לפי המיקום שלהם במעלות בכיוון המייצר הרעש שנחקר באותו רגע. אתם יכולים לראות פה במצגת הזו, אנחנו חוקרים את הפרופלר הימני, ואנחנו רואים איך הפרופלר הימני משפיע על הרעש בכל זווית שונה למול הנסיעה. מכאן אני רוצה להתקדם ל-use case נחמד, case study שבוצע במקביל עם נאסא. בעצם כל המחקרים, רוב המחקרים המרכזיים של FlightStream היו במימון מלא של נאסא, לקחו ב-case study הספציפי הזה, לקחו את הרייבן, שהוא מטוס המראה ונחיתה אנכית, שיודע לשנות את כיוון הפרופלורים קדימה. כל זה עשו ניסוי מנהרה במודל של 28.6%, וכמובן למול FlightStream אנחנו יכולים לראות פה את הגרפים של ההשוואות, כמעט אחד לאחד, שזה מאוד מאוד מרגש מאמר מאוד מעניין, אנחנו כמובן נפרסם אותו גם אחר כך, למי שירצה לחקור, ניתן גם לראות את השפעות הרישות, ואת כל עולם ה-FSI. מכאן אני רוצה להתקדם בבקשה לדוקטור ויבק, שייכנס כאן לדברים, לקרביים של הדברים, יראה לנו ממש בתוך התוכנה, איך נראה התהליך, מה התוצאות ומה אנחנו יכולים לקבל מפלייטסטרים. אז ויבק, I give you the mic. Thank you for attending, and please share your screen and take control.
Okay, fair enough. Let me share my screen here. Okay, can everyone see my screen? Okay, all right, so what I'm going to do for the next 15 minutes here or 10 minutes here, I guess, is just show you what FlightStream looks and feels like. I mean, you've already seen Tomer talking about the capabilities of FlightStream, so I thought it'll be good for you to see what FlightStream looks like when you try to use it. Okay, so what we're going to do is I've got 3 or 4 different cases that I want to show, but we'll start with something simple. Like, for example, I've got here this half model of a Predator drone. And so this model was built in VSP, and I'll switch on the grid view here so you can see what type of grid gets created for FlightStream, okay, on this model. So this one has already been created. It's a half model, so we will do a symmetric longitudinal simulation. In FlightStream, you're able to actually go ahead and create, all the different, split out all the different components, as you can see over here. So you can click and drag and, visualize all the different components. And this is how, as Tomer was saying, that in terms of extracting loads and moments, etc., when we get to like control surfaces and so forth, you're able to get component level loads and moments, not just the overall aircraft loads and moments. In terms of boundary conditions, there's no volume mesh, there's no far field domain. The only boundary conditions we need to apply, and these can be auto-detected, are these trailing edges. And FlightStream can handle both blunt and sharp trailing edges. So that's another benefit of FlightStream over the older generation of panel methods. We apply the free stream, we apply the fluid properties, very similar to a regular CFD setup, except, like it's more lightweight. Down here, as Tomer said, we have the time domain and the steady state simulations. This is where you choose them, right? So depending on what type of simulation you're doing, this one is set up for steady state. So again, just expanding on the conversation earlier about the viscous analysis, this is where you can choose boundary layers, type viscous coupling, and flow separation models, right? So the idea here is that if I want to initialize and run this thing, the slide that Tomer showed on selecting all the based on velocity, this is where you make those selections. You're able to choose between purely incompressible to subsonic, transonic, all the way to supersonic, hypersonic. So this one, let's do a subsonic simulation here. We'll select all the components. We'll select the mirror symmetry as another slide, as we mentioned earlier about turbo machinery. You can also do periodic simulations there, but we'll focus on mirror symmetry for right now. Okay, and I'm going to go ahead and click initialize. Now, when the solver initializes over here, down here is where you can choose, for example, the number of parallel threads, what type of reference properties to use, what angle of attack to specify. So as you can see over here, I've set it up for 5 degrees angle of attack. And in the solver window, you can now see, I'll go ahead and click run. So we'll talk while it's running. Basically speaking, you're able to compute, just like regular CFD, all the different parameters for surface pressure, etc. So you can see that it's going through the solution process. You can see the pressure distributions on all the different components and how they look. Okay, and then the wake will start off as a prescribed wake, as you see over here. And then as the solution approaches convergence, it will relax and do a solution there. While this is running, you can actually go ahead and plot all other parameters as well. So all surface properties, velocities, Mach numbers, boundary layer properties, etc., can be done over here. You can also track the convergence history over here for the plots. So you can see how quickly it converges. And you can see over here, I'm running this on my laptop, and it's already reached about 1E-6 convergence while we were talking. And then we'll give it a few more seconds here. There we go. Okay, so you can see that it essentially does the wake relaxation and computation as well. So the point is that once you get this stuff, and you can see the roll up and the vortices, etc., basically just under a minute in terms of runtime, you go to analysis. This is where you can refresh the spreadsheet and get, as we were saying before, component level information in any coordinate system that you create. So you can create, for example, additional coordinate systems, etc. Okay, so this way, not only are you able to extract the integrated forces and moments, including lift, drag, etc., you can change the units, you can export out to different file formats. We talked about the structures thing, so you can export out Nastran, BDF files, TechPlot, VTK, FEM files, etc. You can also do interesting post-processing. So for example, if you want to know what the load distribution on this wing is under this flight condition, you simply have to go to surface sections down in post-processing. Let me collapse some of this. Okay, and say new distribution. You select, for example, the wing. You select how many points you want. You say create, and it creates those those sections over there that you can then go to plots, right-click, and say show me pressure distributions, and you get all that. Okay, and these can then be used to generate sectional loads, exported, etc. So all sorts of information that you need for design level comes out very, very quickly. Everything I'm showing you right now is also fully scriptable. So you're looking at the main user interface for FlightStream, but everything can be scripted up so that you can then run it through either Altair Compose or MATLAB or Python, whatever programming environment you're comfortable with. The API for FlightStream scripting can support that. Okay, so that's a simple steady state type simulation. Let me show you, for example, another simulation, which is this one right here, which is actually a paper that I'm presenting literally in 3 weeks at the AIAA SciTech conference on the store separation problem using a 6DOF. So the only difference between this one and the Predator simulation I showed you, the mesh and everything is all very similar. The difference is that here the solver is set to unsteady. Okay, and so this is where we are able to specify delta t's and time-based information. All the other properties are similar. Okay, so it's a very simple switch between steady and unsteady in FlightStream. And then down here in the motion, this is where you can specify those motion definitions that Tomer showed in his slide, is that, between Euclidean motion for standard rotation translations to custom motions where you can load up a table lookup for like forced oscillations or prescribed trajectories. And for this one, we have a 6DOF motion that's set up over here. So the way this works is you create a 6DOF motion, you can link it to geometry components that are going to undergo the 6DOF motion. So as you can see over here, I've got the store body and the fins applied over here. You specify the mass, the products, moments and products of inertia vectors. You specify, the coordinate system that corresponds to the CG location, the body coordinate system. You specify gravity, okay? And then over here, you can specify external forces. So as you know, for all these 6DOF simulations and store separation, there's some ejection forces from the pylon that need to be simulated. You can model them here as either force versus distance profiles, force versus time, constant forces, or spring ejections. Okay, so this is all catered towards this kind of store separation type problem. You can also disable or enable 6DOF parameters. Okay, so you can make it a full 6DOF, or you can make it a 3DOF, 1DOF, depending on what type of application you might be working on. So once you set that up and you go ahead and run, essentially speaking, it runs for as many time steps as specified here. Now, obviously, for the sake of time, I'm not going to run that live, but I'll show you what it looks like on this one. Okay, so this is the, and this is, by the way, run at a transonic speed at Mach 0.95. Okay, so that's one of the big advantages of FlightStream, is that we have the transonic solver as well as all the incompressible other solvers as well. And so you can see over here that this case that has been run and the trajectory has fallen to this location. If you go to the plots, you can plot the 6DOF trajectory information and track, for example, what the pitch rate was, or what the change in Euler angles is, pitch angles, yaw angles, all the kind of 6DOF trajectory information. I think I was explaining to Tomer as well that we are presenting this paper that has the summary of all this, the setup, and I'm happy this is publicly shareable. And so in this one, we talk about the setup that I just showed you, but more importantly, just jumping ahead to the results, you can see essentially comparisons with the experiment, because this is a U.S. Air Force experimental data set, and you can see the trajectory and how it compares, with experiments. So we get within a few % of what you get with high fidelity CFD tools. Okay, so that's the most important point. Moving on to a different type of application, I want to show you another one, for example, which is, we talked about, downstream effects between propellers and wings. This is an example from a different paper we did with NASA. So this is from the X-57 program. Okay, and on this one, essentially, you can see there's a propeller in front of a wing, okay, that's been modeled. And again, this is a time domain simulation, except that this time, instead of a 6DOF, we have a Euclidean motion. And Euclidean motion is basically standard rotations and where translations, etc. So you choose the coordinate system and you apply the corresponding motion. So in this case, you can see that the motion has been applied to the prop. Okay. And so what that does is, so if I again show you what the simulation looks like, and you can see that I ran this on my computer just a few minutes ago, took about 4 minutes to run, is you can see the slipstream that it generates and the downstream effects that it creates on the wing. So I'm plotting here coefficient of pressure, which let me make the font size a little bigger over here so that we can see this a bit better. Let's see. Okay, so you can see I'm plotting coefficient of pressure over here. So you can see the slipstream effect that gets created on the wing, as a function of time as the wake propagates. And so FlightStream's ability to propagate this wakes through solid bodies, etc., is automated. So as a user, you don't have to worry about what that wake will do. You simply apply the motion and let FlightStream figure out where the wake goes. Okay. And then the last thing I want to show is, going back over here, I'm going to basically back out from here and pull up a different simulation file where we talk about the structures interactions. So if we pull up, and here I have a very simple example to show you. So this is just a very simple rectangular wing. Okay. And what I would like to do is have a beam applied on it for the structure and do a coupled simulation where the wing becomes flexible. Okay, so to do that, it's a very straightforward setup. It's a steady state wing, etc. But we have two boxes here where you can do like stability and control, acoustics, aeroelastics, etc. And if you go to aeroelastics, okay, you can essentially couple FlightStream, through a command line interface with any other FEM tool, right? So whether that happens to be Altair's OptiStruct, some simple beam code that, for example, has been created here, maybe in MATLAB, Python, wherever you like. And then you can send to that FEM code iterations of loads from FlightStream. So at every step, every iteration, FlightStream will send the loads to the FEM solver, interface with it, and get the displacements out. So the way that works is if you see these points down here, these are my points on a beam, okay, that have been specified. So these are the structural node points that we will interface with. So what you do is we basically just initialize the solver, okay, and I'm going to go ahead and switch off the symmetry boundary here so we can see what's happening to the beam inside as well. Okay, and so because of the interface that has been set up between the wing and the and this beam, when I go ahead and click run, okay, you'll see that the wing does a solution, and then as you can see, the beam bends, and so does the wing, because of the the mapping and the morphing algorithm that Tomer was talking about before. So if I just go back and switch on the symmetry boundaries, you can see this. So these kind of simulations, for relatively simple stuff, has already been validated. We have validation data that we can share. And we're currently in, we've demonstrated the coupling between FlightStream and OptiStruct. So both are Altair products that you have access to. And so if you are interested in, for example, aeroelastic analysis, or even just standard FSI, where you just want to see the flexibility of the geometry and what effect it has on the airplane performance, you can do that very easily with FlightStream. So I think that's the 4 cases I wanted to show, just to give a quick, view of FlightStream.
Perfect. Thank you very much, Vivek. Let me ask you a few questions using those screens. So what can you tell me about the ramp up within this tool? How long does it take to learn it?
Yeah, so again, because we are only talking about, for example, a surface grid and not a volume grid, I mean, right away, there's a big difference right there. We don't need watertight geometry. We don't need the user to know about how to generate a detailed volume mesh, right? So all they need to do is either use something like HyperMesh from Altair, or use one of the FlightStream's own CAD and geometry pre-processing tools. So we typically provide training and support for new users, right? And so our experience shows that about 2 to 3 hours of working with them, they're already comfortable with how to make their geometry. Once you make the geometry, then the rest of it literally takes 20 minutes because it's just there's very few options and stuff. There's not too many knobs and dials to turn, essentially. So yeah, so a few hours in, I think we can ramp up a new user from scratch.
That's unheard of. So one more thing I get asked a lot. This is panel method. We are familiar a little bit with panel method. Can you elaborate a little bit about the validation of the tool using the viscous coupling specifically?
Yeah. Right. So basically speaking, for just like I showed you this paper right here, there's actually several other papers we have published at AIAA last year where essentially speaking, we have validated the boundary layer in FlightStream. So when you do a solution like this, what you're able to see is, for example, if you plot momentum thickness or the key boundary layer parameters, the viscous parameters, we are able to extract that from FlightStream, and we've done validations where we have compared it with known wind tunnel measurements for the thickness of the boundary layer, the velocity profile, etc. An important point here is that FlightStream does not assume some empirical model for skin friction coefficients and drag. Okay, it's actually a numerical model that's very similar to RAN CFD. Okay, so that's what we compare with, and there's a couple of papers that were presented last year where we have done that, as well as one from our customers that was an independent validation study. So all of that we can share.
Well, that's perfect. That's perfect. And regarding the flow regime and the fluid itself, I know that FlightStream is about subsonic and ultrasonic. What can you tell me about water fluids?
Submarine or marine applications, you mean?
Exactly.
Yeah.
Exactly.
Yeah. So the only difference here between those. So okay. So we all for incompressible stuff, you can actually set it to fully incompressible. Okay, and when you can select the fluid over here to change it from air to water. Okay, we've got several submarine type validation studies that we can share because I mean, if you're doing a subsea application, that's no different from an incompressible, air application. Okay, and so all the 6DOF stuff, all the basically the motion stuff, as well as steady and unsteady, remains unchanged. The only thing that we are still working on right now that will get released next year is free surface modeling, so waves and hydrodynamic resistance. So that's in a prototype stage right now, and we're expecting that 25.1 or 26.0 version of FlightStream next year will have the the ability for hulls, etc., to move at the interface between the water and air.
That's perfect. That's very exciting. One last thing before we close. Can you show a little bit about the hinge loads and how you investigate hinge loads within moving objects?
Right. So, okay. So basically speaking, when we get to, let me open up a different simulation file here so that let's go back to that predator example that I had before. Let's see. So let's say, for example, that, give it a second here. Okay, so let's say that you have a geometry like this, where essentially speaking, the user has brought in a clean wing, okay, and now they decide that they want to do studies of control surfaces, layouts, hinge moments, etc. So the way that works is that you are able to, once you import the geometry into FlightStream, you're able to go into CAD over here, and I'll just show you a very, very quick setup here. So for control surfaces, so let's say I do one for wing, where I'll just do, oh, sorry. Wrong direction. So that's Y and on wing. Okay. So what it does is we create cross sections of the components, okay, that we are interested in. Okay. And so we are able to do that in FlightStream. And then we are able to assign those cross sections, to either a wing or a fuselage type component up here in our CCS tool. When we do that and we assign it, we are then able to add control surfaces and flaps and other things rather easily because it's parameterized. So it's essentially you're able to tell FlightStream, this is a wing, that's a fuselage, this is a rotor. And so once that intelligence has been added and that parameterization is done, it knows that you're talking about chord and span, etc. So then you can add control surfaces parametrically in any layout that you like, combination of fully gapped, partially gapped, flaps, morphing, like there's all these different options over here. And for each one, you're able to specify, where the hinge line is going to be. Okay, so you specify the size, the deflection angles, all of that, the details for the flaps and simple control surfaces. And so once you do that, okay, then you're able to extract, for example, the corresponding hinge moments. As an example, let me just show this real quick. So I will add here very simple control surface. Okay, so we will add it from depth, span-wise coordinates of 0.5 to 0.7, and I will do it from 0.2, 0.2, so that's the 20% chord depth. We'll put the hinge at 50%, and we'll do a deflection down of let's say minus 10 degrees or minus 20 degrees. Okay, and so if I say create, done. And so if I'm going to go ahead and uninitialize this, okay, and what I'm going to do is I'm going to go ahead and hide this wing, okay, and create a new one over here. So let me just hide all the other stuff so you can see what I have created here. Okay, so you can see that essentially speaking, based on that parametric information, it's created that wing with that control surface already deflected. And more importantly, you can see there's a hinge line in there. You see that, this coordinate system? And so that means that when I go ahead and do my analysis, so if I just do my a quick analysis here with this thing, so we will, and I'm skipping through a couple of steps here, but bear with me. Okay, so I've initialized just a simple wing over here with these control surfaces, etc., and we'll do a quick solution here. So you can see the pressure distribution evolving. And then when we go to the analysis, what I'm going to do is I'm going to switch to that subsurface hinge axis. Okay, so I think it's almost done here. So we'll give it a second. Yeah, there we go. So you can see that I've done a simulation, with these control surfaces deflected. And so what I can do now is when I refresh the loads, I can then say, okay, I just want the contribution of the subsurface, not the the wing, etc. And I want it in the subsurface coordinate system. And because the x-axis corresponds to the hinge line, the corresponding moments is your hinge moments. You see what I'm saying? So rather than give you a verbal answer, I think I just, I just showed you how to do it. But that's, yeah.
I think it was best. We also have, thank you for that. We also have a question from the crowd asking about unsteady aeroelasticity.
So yeah, so when I was, actually, I think I closed that file. Let me well, actually, I don't need to reopen that. I can show it here. So when we talk about aeroelastic coupling, right, that toolbox that I showed you, it is also enabled in the unsteady solver. So, so if you are running an unsteady solution, you simply have to check that box and say that whatever aeroelastic setup has been done here should be also applied when the time step, that is being used in the unsteady solver.
Amazing. So essentially, yes, we just need to remember to toggle the check mark.
Yeah.
Perfect. Okay. Do we have any more questions for the crowd before we close? חבר'ה, זה הזמן לשאלות, מי שרוצה לשאול, גם בצ'אט. We have a question, Vivek, asking about supersonic velocity. So, yeah.
So, sorry, what's the question? Like, just want to know more details about it, or?
Yeah, Aviv here is asking if there is one. I will mention that I have mentioned before, we do supersonic, but maybe you can elaborate a bit more about.
I can. So, and again, we can also send some slides on this as well. So basically about just a bit of history there. We were funded about 3 years ago, or well, 2 years ago now, I guess, from the Air Force, the U.S. Air Force, to essentially add transonic, supersonic, and hypersonic capabilities to FlightStream. Okay, so when we got acquired by Altair, these contracts, which are still ongoing, by the way, have been essentially absorbed under Altair. Okay, and so the transonic solver has been deployed in FlightStream in version 24.1. The supersonic comes in 2 flavors, a high order and a low order, and there's also an early hypersonics capability as well. The hypersonic contract is still ongoing, so we are going to add in early 2025. The plan is to add thermal and trajectory analysis. Okay, but on the supersonic side, the high order solver is essentially the equivalent or subsonic solver, but so linearized panel methods for supersonic flow. That works well for about Mach 1.3 to about Mach 3 or so. Basically, like for a supersonic aircraft rather than missiles and other things. For missiles and munitions and stuff, we can actually use the low order supersonic method because that's like very, very rugged, and you can throw anything at it and you will get a solution, right? Whereas with the higher order solver, it's a more careful setup because you have to be, you can model more realistic geometries, but you have to be careful with your setup. And there's a restriction in terms of it can only work between 1.3 and 3, Mach 1.3 and 3. The supersonic low order can start right at Mach 1 and go on till about Mach 20. So there's an overlap between the low order supersonic and the hypersonic solver. By the way, the hypersonic solver is what you want to use anything after Mach 4. And so we've done some validation studies that we are again presenting in 3 weeks at the SciTech conference in January. Is essentially the same geometry, the same mesh can be run entirely from incompressible all the way through hypersonic. So you don't have to make changes to the mesh, except, like I said, maybe for the high order supersonic, you just have to be careful about, the shocks and other things that we capture. But everything else, you can take the same exact mesh and run it through the setup. So there's not anything special to say about it. It's already there. It's available to you, to use today.
Thank you very much for that. We have a few more about regarding FSI analysis. Can the structural stress be represented?
Sorry, can you repeat the last part? Can what be represented?
The structural stress. Oh, where do you see it?
Yes, so not directly. I mean, so at the end of the day, FlightStream is doing a time domain CFD-like solution, right, for the flow. So our conversation with Aeroelastic Toolbox is essentially in the context of us sending the FEM solver some the load distributions, and the FEM solver sending us back displacement vectors for the key structural points, essentially, right, the structural node points. And then we map those displacement vectors from the node points over to our surface mesh in FlightStream. So that's what you saw in that wing case that I showed you. So FlightStream is not doing any kind of structural dynamics equations internally. Okay, it is entirely operating as a CFD tool that's just retrieving information from the FEM solver.
Okay, so when we would like to see the effects on the structure itself, we will need to see it within the structural solver post-process.
Exactly, yes.
Yeah, that's simple enough.
Oh, actually, and sorry, one point I'll add to that, if you don't mind. You don't have to do the FSI toolbox and have a two-way coupling with flexibility and all of that stuff to communicate with the FEM solver. So let's say you have an FEM solver, Nastran, OptiStruct, whatever it is, and all you want to do is run this predator case and send out load distributions or pressure distributions, etc. You don't have to couple it with FlightStream. You can simply export out load distributions from here. For example, we write out Nastran BDF file formats that will load up in OptiStruct as well as Nastran. So if you just want to transfer load distributions from FlightStream, you can absolutely do that, right? You don't need the two-way coupling. And you can also do it via probe points down here. So you can load in a Nastran grid file into FlightStream and map the distributions from the FlightStream mesh onto the Nastran mesh. So I say this because, not every simulation needs to be full-fledged FSI. It can be more simpler than that.
Of course. We have a question regarding thermal heat transfer. I will mention that I can answer part of it. We only do external aerodynamics within FlightStream. This is not regarding any internal aerodynamics. But do we have heat transfer in the external, Vivek?
Yeah, so the boundary layer models, only in so much as surface heating is concerned. Right, so the effect of that on the boundary layer, that's what I mentioned for example, for the hypersonic and supersonic stuff, where that becomes like really critical. So we can share, we're presenting yet another paper on this at SciTech, explaining our thermal models, but I can send you guys a copy of the PDF. So basically speaking, all we're doing is we're assuming that based on the skin friction and heating, the surface heats up, and based on that, it has an impact on the boundary layer and the viscous characteristics, which in turn affects the aircraft aerodynamics. Okay, so that's the limitation on what we're doing.
Understood. And another one we have over here is aero servo elastic analysis. Can it be performed? How complex it is?
That's a good question. Given how scriptable FlightStream is, I mean, there's nothing preventing its implementation into an aero servo elastic environment. My suspicion, though, is so we don't have any toolboxes directly inside FlightStream for aero servo elasticity. But the point I made earlier about everything being scriptable, so that you don't actually have to sit and do a point-and-click type setup like I'm doing right now, means that you should be able to embed FlightStream inside that kind of a, let's say you have a MATLAB environment or Python environment or Simulink environment, let's say, then you should be able to go ahead and embed FlightStream via scripting to get the aerodynamic loads. But but there's nothing inside FlightStream that specifically caters to that.
So that would be a part like of a sort of maybe even a digital twin within Twin Activate, having a system of systems running Flux and OptiStruct and FSI together or something like that.
Exactly. Because and I mean, the fact that we can do control surfaces, hinges, all that stuff is really nice, but it would have to be under some other environment where you're calling FlightStream to, give you the aerodynamic performance for that particular instant.
Yes. And when we spoke earlier about hinges and hinge loads, can we take in point the flexible hinge, or is it only hinges?
No. The morphing and mapping algorithm that I showed you and stuff for the FSI, that also applies to our hinges and to our control surface modeling. We haven't done a validation on that yet because that's a pretty interesting topic, and I'm not even sure if there's validation data necessarily out there for that. But Yeah, we haven't gotten to it yet, but that's very much on our list of things. Yeah.
Perfect. So not only rigid bodies, also flex bodies for the hinges and the servos.
Exactly. Yeah.
Yeah, I think that would be our last question up until now, unless anyone wants to chime in, מישהו רוצה לקפוץ עם איזו שאלה אחרונה לפני הסיכום, זה הזמן. הופה. Is it possible to be connected to motion solve? So like we mentioned, we spoke about it earlier, the ability of creating analysis on the hinges, on the movable objects, a coupling with motion solve would probably be unnecessary. Other than that, we can couple with Twin Activate and a system of system simulation to see how it conveys. But I do believe that you can receive anything you would need for servo analysis and hinge analysis within FlightStream. It is not needed to be coupled with a rigid body dynamics, since we already have these capabilities within the software.
Correct. Yeah. I mean, FlightStream is very much it comes as a standalone tool because it was built as a standalone tool. So it has its own pre-processing and motion and scripting, etc. Over time, we will expand our connection with other Altair products. OptiStruct is already happening right now. HyperMesh is already there. And then, Motion Solve is on our list. Yes.
Awesome. Okay, last question. How is software? Okay, so they're asking specifically comparing with LES or RANds, how can we predict a shock wave?
Yeah. So basically speaking, so let's put it this way. So there are two answers to that question, or well, three. For transonics, we are using the field panels method to actually capture the shocks. And actually, that's not something unique to FlightStream that has been shown to work for other panel methods in the past. And so you can actually, we compare very nicely, I guess, on the shocks for, using field panel methods. Where I think for same thing for the supersonic linear methods that I showed you, there's actually some slides that we can send where you can see a full volumetric shock. The nice thing about this whole implementation is that even though you're getting data on the surface, it's really not restricted to the surface. You can create, for example, off-body, on-body, and then volume sections over here to visualize the volumetric flow. And when you do that with the supersonic solver, you actually see the proper shocks that come out of FlightStream. The place where we don't have extra, volumetric analysis capability for shocks is the low order supersonic and hypersonic solver, which are entirely based on modified Newtonian methods and tangent cone methods, etc. So which means that they can give you the effect of shocks, other things on the surface, they cannot visualize or capture the shocks at all. So if you're using one of the low order solver modes in FlightStream, you won't get shocks. If you're using the higher order solvers or the transonic solvers, then you'll be able to visualize shocks.
Perfect. Okay, I think that's it for today. We went over a bunch of stuff. This is recorded, so don't worry. Webinar מוקלט, בוא שמוליק תוכל...
Thank you, Tomer. Thank you, Vivek, for your time, for all of your explanation. חבר'ה, קודם כל, תודה רבה לכם על השאלות. כמו שהתחלנו ואמרנו בהתחלה, המוצר הזה, הטכנולוגיה הזאת היא מצטרפת לחלק מפורטפוליו המוצרים של אלתר, היא נגישה ברישיונות שלנו, בפילוסופיה שלנו בעצם יש אינטגרציה מלאה בין הכלי לבין כלים אחרים, ולכן היא מייצרת נגישות ואג'יליות מאוד מאוד גבוהה. אנחנו נשמח להיות עמכם בקשר עם מי שזה רלוונטי לו, לעשות פגישות המשך, לצלול לגבי הקייסים הקונקרטיים, וזהו, אנחנו פה מהבחינה הזאת, נעביר לכם כמובן בהמשך את ההקלטה של השיחה. תודה לכולכם על הזמן, זמינים לכל שאלה במיילים או בטלפונים, שיהיה לכולנו שבוע שקט ורק בשורות טובות. להתראות.